So I've been asked today to talk about how we can use some simple mathematical models to help us to understand and predict the spread of infectious diseases. Now I promise to keep the math to a minimum so you won't need a PhD to follow along, and instead I will illustrate the concepts using some interactive visualizations. My name is Eric Westhus, and I joined RGA as a data scientist during the summer of 2017. And I really became interested in these models as a graduate student when I was at St. Louis University studying mosquito population dynamics. And I won't talk specifically about my dissertation work here, but I will share some of what I learned about these models along the way. So compartmental disease models have been in development since really the opening of the 20th century. And some of the early work was done by a physician named Ronald Ross and a mathematician, Hilda Hudson. And together they were interested in understanding the transmission of malaria. And a few years later, a biochemist by the name of William Kermack and a physician, Anderson McKendrick, built upon those models to derive a set of equations whose form are really going to be close to the ones that we'll look at today. And so compartmental models are used in a variety of fields, from physics to economics to biology, epidemiology, lots of different fields. And the idea is really to understand how individuals flow from one compartment or state to another. And what makes these models so powerful is that they allow us to simulate a system, to simulate an outbreak, and in doing so we can answer questions that may enable us to shorten the length of an epidemic, to reduce the number of people who get sick, or even really stop an epidemic from occurring altogether. And insurers in particular can use these models to quantify the risk posed by pandemic tail events in order to ensure solvency. So this is a textbook SAR model. It represents a population of people who flow from one compartment or box to the next, and it's generally assumed that everyone starts in the susceptible compartment, except for one individual who's going to start in the infectious box. This is our patient 0, and he introduces the new disease into the population. And now as susceptible individuals become sick, they're going to join patient 0 in the infectious box until they either recover and acquire immunity or they die. In either case, we say they are removed from the infectious state, and they're no longer susceptible to acquire the disease again. So this follows the classic immune response, where a person's immune system fights off an initial infection, and then in doing so creates antibodies for that infection that allow it to fight off future exposures without getting sick again. Over any time interval, a certain percentage of individuals will move from one state to the next. And the rate at which individuals move from susceptible to infectious is going to be equal to the number of possible encounters. We calculate that as S times I, and then we multiply that by the proportion of those encounters that result in infections. We'll call that portion beta. The transition rate out of the infectious box is just the number of infectious individuals, or I, multiplied by the proportion that recover during that interval, and we represent that as gamma. So with those transition states in mind, we can mathematically define an epidemic. Anytime people are being infected faster than they are recovering, you have an epidemic. But anytime people recover faster than they are infected, the epidemic burns itself out. So in other words, if the rate going in divided by the rate going out is greater than 1, we're going to have an epidemic. But if the ratio is less than 1, it's going to burn itself out. So that's a really beautifully simple way to describe an epidemic. And the reason for that is because it tells us exactly what we can do to stop an epidemic in its tracks, or it can even help us to prevent one from occurring in the first place. All right, so if we can lower beta, that proportion of all possible encounters that actually results in transmission, then we can slow the epidemic. Well, how might we do this? Well, beta is actually the product of two other proportions. The first is the proportion of all possible contacts that actually occur, and the second is the probability that any one of those contacts is going to result in transmission. So quarantine could lower the number of actual interactions that take place, and prophylactic measures such as hand washing and disinfectants could lower the chances that any one encounter would result in transmission. Next up, gamma can be thought as the inverse of the duration of an infection. So by seeking immediate medical treatment, it's sometimes possible to shorten the length of an infection and thereby helping to more quickly end an epidemic. The last variable in that ratio is S, and as we will shortly see, S is going to decrease with time as people move out of that S box and into the infected box. So our ratio is not constant, and eventually our ratio is going to always drop below 1. But what if we could skip the infectious box altogether and move people from S directly into R? our ratio can be shrunk dramatically without having any infections, and we could start out in a much better place. So this is exactly what vaccinations do, right? So in fact, if enough people are vaccinated, they can start the ratio below 1. Patient 0 can sneeze all over everybody in the subway, and we're still not going to have an epidemic. This is what we're going to call herd immunity, and it's why vaccinations are so powerful in preventing epidemics. To actually build a model of an outbreak, we need to estimate the initial values for beta, gamma, and S. And then we can set up some equations that will mimic the flow of individuals from one compartment to another. We get the population density from the size of our population, and that's going to give us S. And we assume that patient 0 is the only one who is going to start with the infection. We're going to assume that nobody leaves the population or immigrates into the population. And that's sort of admittedly a naive assumption, but for the purposes of a simple demonstration, it works pretty well. All right, and then we estimate gamma and beta from our prior knowledge of similar diseases. Gamma is, again, just the duration of the infection, or rather the inverse of the duration of the infection, and that's pretty easy to measure. And then beta is going to be calculated from something called the basic reproductive rate. And this is known as R naught or R sub 0. And it's simply the average number of new cases that will be caused by patient 0 over the course of his infection. R naught is really just the starting value for that ratio, because at the start, everyone is really susceptible. And then lastly, we're going to use a computer to solve some differential equations that actually model the flow of individuals. The exact form of those equations are sort of beyond the scope of what we're doing here today, but on the right there you can see my programming script, and maybe you can pick those out for yourself. So this is a simple SAR model that I've programmed, and it really tells a story. So let's say that you are a college student on your way back to your dorm after your winter break, and you get on a plane, and the person next to you has the flu and did not have the good sense to quarantine himself. And so he decided to lock himself into a plane with you and 200 other susceptible individuals. Thanks a lot, dude. So what happens? You are going to become infected with that flu virus, and you're going to bring it back to your dorm of, let's say, 200 individuals. And over the next 4 days, let's say, you are going to infect let's say 3 other individuals, your roommate and your 2 neighbors. And so what this model is going to do, it's going to help us to tell the story of the next 30 days. And at first, we can look at this red line here, and you're the only one who is infected. But then your roommate gets infected, and your neighbor gets infected, and pretty soon people are getting infected faster and faster. Instead of a new person coming down with a disease every day, it's every hour. And until about day 10, when 25% of your dorm is infected, about 25% of the dorm has recovered, and the remaining 50% is ready to drop, and 100% of the dorm hates their guts for bringing this thing into their building. And so it continues to rise, and you feel better, but everybody else is getting sick until right around here at day 12, when an interesting thing happens. The infection rate starts to slow. Instead of people getting sick every hour, people are going to start to get sick every day, and then every other days. And what's happening is that ratio, that beta to S over gamma, has dropped below 1, and the epidemic is starting to burn itself out. And eventually, around day 30 or so, the infection, the epidemic has burned itself out, and there's about 3 people who were probably holed up in the basement of one of the science buildings who managed to escape the outbreak. But what happens if, let's say, your RA convinced everybody to stay in their rooms instead of walking around? Well, look what happens. We're going to drop beta down a little bit here, and now only we have the disease, the epidemic progresses much more slowly. We might have to go out to day 60 or so to see what's happening. And sure enough, it takes until around day 50 or 60 when these things stabilize. About 20% of the 25% of the population never gets sick. And so we've slowed the disease, and we've kind of prevented a lot of people from getting sick. Now, what if everybody calls their doctor and gets on Tamiflu? And so the duration of the disease now is, instead of being 4 days, you're only infectious for 3 days. Well, look at this. Half of the individuals never get sick. And again, we have to go out even farther. Let's say go out 90 days to see what's happening. And sure enough, only about half of the people ever get sick. Now, here's the really fun part. Let's say that the university policy states that everybody should get a vaccination. And they even hired a nurse who was successfully able to vaccinate 70% of the population. Well, look at this. We start out with our ratio below 0. We never get an outbreak. Even if no one gets on Tamiflu, no one gets treated, and let's say the RA throws a party in the basement, we still can't have an outbreak because we've vaccinated enough of the population that people recover faster than they would get sick. And so this epidemic never really has a chance to even get started. And really, that's the power of these models, is it allows us to tell these detailed stories about what's happening using a relatively simple set of equations and very few parameters. So even a simple model such as that, a model that is obviously and intentionally a simplification of a real-world system, it tells a nice little story that enables insurers and the medical community to assess the risk posed by emerging diseases. And while not all diseases progress so simply from S to I to R, that compartmental approach is flexible enough to handle a variety of different disease progressions. So all models are wrong, but some are useful. That's a famous quote by statistician George Box. And what it really means is that we've just talked about a simple SIR model that is a simplification of a real-world system. So it's not true. But it allows us to really get some useful information out of that we can use to assess the risk of an emerging disease. And not all diseases are going to progress so simply from S to I to R. But what's really cool about these compartmental models is that they're very flexible, and they allow us to handle a lot of different types of disease progression. For example, an SIR model might be expanded by including a box for incubating individuals. And these are individuals who've been exposed to a virus or exposed to some pathogen, and they have it, but they're not infectious yet. And so we might model going from susceptible to incubating to infectious and then finally removed. Or maybe we really do want to keep track of who dies versus who just becomes resistant. So now we have a fourth box for the individuals who die from the disease. And maybe if this is also a disease that's going to last for a while, we're going to introduce some births into the system to allow the population density itself to expand. So we're taking that simple model and we are expanding on it in ways that maybe are a little bit more realistic. All right, and now these are my favorite models, the host vector models, as a former mosquito researcher. And these are cool because now we're going to have a pathogen that's going to move from one species to another. And it's not your encounter with another human, but it's your encounter with a mosquito. So a susceptible individual comes in contact with an infectious mosquito and becomes infectious himself. And then that individual has to come in contact with with a susceptible mosquito, who then becomes infectious, and you sort of get this cross back and forth between the two species. So these are really powerful, and there's a lot of different ones like this to model a variety of host vector models. So in summary, I really want you to take away 4 key things from today's talk. And the first one is that insurers and the medical community can really use these compartmental models to assess the risk posed by epidemics and pandemic events, and allow us to plan for severity and put some precautions in place. The second thing is that an epidemic is going to occur whenever conditions allow the infection rate to exceed the recovery rate. And then the interesting property of outbreaks is that they generally end before all individuals become sick, as we saw from our demonstration. And so what that really allows us to do is we can have some interventions that are going to allow us to slow the progress of an epidemic. We can reduce the percent of the population that actually gets sick. And we could even potentially prevent an outbreak from occurring if we can start out with a vaccination rate that's high enough. So, thank you for watching. Please get your flu shot, and do us all the courtesy of quarantining yourself when you are contagious. Thank you.